In this video, we're going to learn how to find the area of a sector of a circle, as well as how to calculate the linear speed of an object traveling in circular motion. But let's start with the area of a sector of a circle. Now, very similar to how we derive the formula for the arc of a circle, we're going to do a very similar ratio to find the area of a sector of a circle, which is like one of these little pizza slice pizzas. Now, I'm going to use green to represent a general angle and area, while A1 and theta will be a very specific one. In this case, we'll let theta 1 represent 2 radians, which we learned in the last lesson is a full revolution. If I use a full revolution, that follows that the area should be the full area of a circle, which will be pi r squared by definition. So, first, I'm going to rearrange this before I plug anything in to make it easier. I'll multiply each side by A1. So I'll have A is equal to A1 times theta over theta 1. Now I'll plug in what I know for theta 1 and A1. A1 is pi r squared, and theta 1 is 2 pi. Now, very nicely, the pi's will cancel. I'll be left with a 1/2, an r squared, and a theta. And that's where you get the formula for the area of a sector of a circle. Now, again, the simplicity of this formula comes from the fact that theta is in radians and not degrees. Now, let's find the area of a sector of a circle of radius 2 feet formed by an angle of 30 degrees. And we're going to round our answer to 2 decimal places. Now first we need to identify what is the radius of our circle. Why, it's 2 feet. Then the angle is 30 degrees. Now, in order for me to use this formula, it needs to be in radians. So I'm going to convert this 30 degrees to radians by multiplying it by pi over 180 radian, as we learned in the previous lesson of how to convert. That'll leave us with pi over 6. So perfect. Now we can go and plug it into our formula. So we'll have A is equal to 1/2 times r squared, which will be 2 squared, and theta, which is going to be pi over 6. Now 2 squared is 4. 4 divided by 2 is 2. So we'll have 2 times pi over 6, which tells me that my area is equal to pi over 3. And if you want a more concrete answer, convert that to a decimal, like this problem's asking for, and we get 1.05 feet squared for the area of that sector of a circle. Now, let's talk about how to find the linear speed of an object that's traveling in circular motion. So there's 2 different formulas we need to talk about. First, it's linear speed, which you often know is just as distance over time. But there's also angular speed, which is the amount of angle change over time. Now, we can do something very interesting by looking at our linear speed formula, which is distance over time. But now, using the arc formula from our previous lesson, we can represent S as r times theta, as long as theta is in radians. It's like I wrote up here. Now, if I write it that way, we see we get theta over time, which is angle over time, which can be replaced with omega, give us a new formula, which is the velocity, or the speed rather, is equal to radius times omega, r times omega. So it gives us a few options to be flexible when calculating this linear speed. Now, A child is spinning a rock at the end of a 2-foot rope at a rate of 180 revolutions per minute. So spin it pretty fast, about 3 revolutions a second. So we want to find the linear speed of the rock when the child releases it. So first we're going to start with trying to calculate the angular speed. Now, we have 180 revolutions in 1 minute. But we want to convert that to radians. Now, we know in the previous lesson that 2 pi radians is 1 revolution. So we can convert that, and that will give me 180 times 2 pi, which is 360 pi. This will be radians. And you'll see here that the revolutions cancel. And then it's going to be over per 1 minute. So there you go. So now our angular speed is 360 pi radians a minute. So now let's convert that into a linear speed. So now, since we know that the speed is equal to the radius times this angular speed, I just need to figure out what the radius is, which I have a 2-foot rope. That'll be my radius. So I can put 2 for r. My angular speed is 360 pi radians a minute. And now when I multiply that together, I'm left with 720 pi feet per minute. Now you may be wondering, where did the radians go? Since radians are based off the arc length, that radius arc length, it's that angle of 180 or 360 pi radians doesn't really have a unit yet. It's virtually unitless. So when I apply this 2 feet to it, it just kind of replaces what that unit was. So now I am left with 2,262 feet per minute, which is approximately, that's pretty fast, but that's 25.7 miles per hour, which I think is a pretty fast throw of that rock.